Hello, Mr. Collier here, and welcome to Kinematics, Episode 2. Today we're going to answer the questions, how far did it go, and how fast did it travel? And if that sounds familiar, yes indeed, these are the same questions we answered in Part 1, but we're going to answer them from a different frame of reference. Today we're going to be talking, instead of a scalar quantity, we're going to introduce something new called vector quantities. So now we're going to introduce a concept called displacement, which we use the term delta x to describe. Again, delta, the little triangle, means change, and we're going to use x instead of d. This x is a final position related to the initial position, and it is regardless of the path. That's the big difference between distance and displacement. And to figure out something's displacement, we're going to look at where it is at the end. We call that xf, as in final position, and its initial position. If you subtract them, you will find the displacement of the objects, and we call that, again, delta x. So let's go back to our example from our previous set of notes, where we were asking the question, I live 5 miles from North Penn High School. Where do I live? So previously we had used this idea of distance to talk about that really anywhere in a 5-mile radius around the high school would satisfy this criteria. But now, what if we get a little bit more specific and we say, I live 5 miles west from North Penn High School. Where do I live now? Well, now we have some specific direction, and so we can hone in a lot more and put a star 5 miles to the west of North Penn High School. Now, delta x, displacement, has both a magnitude and a direction, and that direction takes us from what we talked about last time, scalar quantities, to vector quantities. A vector quantity is one that has both magnitude and direction, and everything in today's notes are going to be vector quantities. Vector quantities, like displacement, have a little hat above them, sometimes people call it. It's like a little arrow, and it indicates that this is in fact a vector quantity. So anytime you see that little arrow, you know that you're dealing with a vector quantity. So now let's look at an example to understand the difference between distance and displacement. We're going to look at the same motion from two different frames of reference to understand these terms. So let's take our dude here and have him do a little walking and discuss his motion. So first he walks 5 meters to the west. So that is on this number line, 5 units to the left. And this is a pretty common convention. You need to set up your frame of reference. When you're doing word problems throughout the year, you're going to want to set up something that makes sense. Typically we do things like west is left and right is east, north is up and south is down. But again, it's all about your frame of reference. As long as you're clear, any of those are fine. Next, dude is going to walk 7 meters to the east. Now on our number line, this is to the right. So you can see dude is now 2 meters to the east of where he started, but he's traveled a lot further than that to get there. Finally, he's going to walk 4 more meters to the east, and the question now is, where have we ended up? So to talk about dude's distance, we simply add up all the units that he's traveled. 5 plus 7 plus 4. He's traveled a total of 16 meters in distance. But his displacement is where he is now compared to where he started. And so for that, we note that he is 6 meters to the right. Now there's really 2 ways that we can determine that 6 meters to the east figure. We can just simply look at the number line that we've been keeping track of, or we can add up all of his distances but take into account the direction. So west was negative and east was positive. So -5 plus 7 plus 4 gives me 16. And that illustrates the difference between distance and displacement. So now that we understand that displacement is a vector quantity, let's look at the equivalent when we're talking about how fast something's moving. Instead of speed, a scalar quantity, we're going to talk about velocity, which is a vector quantity. In your daily life, you might use speed and velocity as if they mean exactly the same thing, but in physics, they are different. Velocity is how fast and in what direction. In other words, it's the vector version of speed. There's a couple different ways we can write the equation for velocity, but all of them come down to displacement over time rather than distance over time. So here in one version of a velocity's equation, we have delta x over delta t. In other words, the change in displacement over time. And one way to talk about change is final minus initial. So you'll see in this equation I use little f's for final and I for initial. If you know where something was and where something is, you can figure out how much it has changed. Other times you might see this same equation written out with, instead of final and initial, you see it with a little 0 subscript for original and x for where it is now. And a third way to calculate average velocity is simply to take the final velocity, the initial velocity, add them together and divide by 2. That's your more traditional way to calculate an average, is add them up and divide by how many you have. This, however, only works if we have a constant acceleration, and so you're going to see that there's only certain scenarios where we use this. Alright, so now let's do an example of calculating average velocity. Let's say our green racer drives 80 kilometers west in 1 hour. Then he turns around and drives 70 kilometers east in 2 hours. Let's find both his average speed and his average velocity. Now, if we recall, average speed just looks at distance traveled. So he drove 70 plus 80 kilometers. He drove a total of 150 kilometers, and his total time was 3 hours. So we take distance divided by time, and his average speed was 50 kilometers per hour. But when we're looking at velocity, we need to consider his displacement. 80 kilometers west, we'll call that negative 80. 70 kilometers east, we'll call that positive 70. His displacement is actually 10 kilometers to the west. Now we can write that 2 different ways. We can keep talking about the direction. He ended up 10 miles west of where he started. Or we can talk about it in terms of a positive or negative. We called west negative. Either way, it's 10 kilometers over 3 hours, so our number is the same, 3.3 kilometers per hour. But the difference here is whether we indicate our direction with the word west or with a positive or negative sign. The positive or negative side hinges very importantly on your frame of reference, so it's important that you indicate that through either a picture or some other indication. Either way, we're now realizing how different speed and velocity can be. The last thing I wanted to mention was instantaneous velocity. Much like instantaneous speed, it is your velocity at a particular point in time. And so when you're looking at a speed limit sign, that's really saying at any instantaneous moment, you can't be going above that speed or that velocity. It's calculated using calculus as well, and so we're not going to be calculating it strictly speaking, but we will be discussing it and working with it some this year. Hopefully now you realize that there is more than one way to answer the question, where am I and how fast am I going? And we've given you ways to talk about that both in scalar terms and in vector terms now.